Good morning and welcome back. Today, we will continue our discussion about radiation by moving charges. Last time, we talked about the first class, we talked about linear charge potential. Then, we derive E field and B field due to the potential. It's classified into two parts. One is velocity field. The other is acceleration field. Velocity field and acceleration field. And we consider the velocity field, constant motion last time. Today, we will consider total power radiated by an accelerated charge. Accelerated charge or decelerated charge, 加速或减速，加速或减速。Total power radiated by an accelerated charge. That's ED220531 okay? And we will use a very special techniques. We reduce to traditional case. And then try to generalize the case to special relativity, to very high frequency. That's very smart. Okay, but before that, let me show you an animation. Let's change to this one. Okay. This is the animation. Look at this figure. Look at this figure. A particle, constant motion, and suddenly stopped. So just like acceleration, it will already, when it stops, it generates fields. The field lines and the modulus of the electric fields generated by a charge, negative charge. First, moving at constant speed and then stop quickly to show the generation of Brewster radiation. Brewster radiation 突然减速到零，所以就有很像 radiation 出去的。Okay. Go back. Go back to iPad. Oh, sorry. Go back up. I make a stupid mistake. Go back to iPad. The field, when the particle is suddenly accelerate and decelerate, it's completely different. Deceleration and acceleration will cause some effect. Okay, just a moment. Just a moment. Because I switched from notebook to computer. Okay. So we just show you the animation. Now, it divided into two parts. So we have velocity field, 1 over r squared, and acceleration field, 1 over r. So you can imagine the pointing vector is E cross B. This one will contribute to r to the square force. And this one is 1 over r squared. If you integrate the surface, then this one will be the most important part. This one is the major contribution is from this one. Okay, so therefore, acceleration field is the most important part of the radiated field. Okay, so let's consider Poynting vector. That's Gaussian unit, E cross H SI unit. And this one is, if B is equals to this one, M prime cross E is M prime. So eventually evaluate at this case, 1 over C E X T Poynting vector is in the N direction. If you don't remember, oh, here is the N direction. This is the acceleration. Okay, first, let's reduce the problem to Lamo's formula. Neglect the velocity field because, as I just shown, the velocity field is relatively small if R is very, very large. And we take the limit, beta equals 0. Then, that's very slow, extremely slow. So we have electric field. We got only one term, beta very small, beta very small. So I'll drop this term. So, okay, very, very small. Therefore, this one becomes N cross beta dot. And here we have one, just R only, but R only. Where is the R? Here. R times C, E over CR. Yes, correct. So the Poynting vector x dot n is radiated from this point, and Poynting vector x. We have a Poynting vector x in outer space. And observer is here. So s dot n will be here. Very simple. Because this is n, this is n. These two are the same and exactly the same. Therefore, we have electric field only. And power per solid angle. Power per solid angle. Power per solid angle. The power is the Poynting vector times R squared. Solid angle, 4 pi R squared to be integrated. R squared here. So it's E squared over 4 pi C is this one. This one gives us just one term. N cross beta dot squared, okay? And N cross beta dot is beta. Remember, beta dot is V dot over C, okay? So we just change this one C squared here to here. 1C plus another C squared. So we have C cubed, E squared, 4 pi, V, because of this one. N cross beta is cross, so it's sine theta. Theta is the angle between N and beta. So it's power radiated per unit solid angle peaked. So the maximum value will be pi over 2, right? That's the maximum value is 1. Maximum value is 1. Okay, move on. Total power radiated. Once again, we should perform the integration. and eventually it will be related to here times 4 pi. So V dot can be rewritten into V in the classical limit. And M over P dot. What happened? Oh, sorry. M over P, P dot. So it can be right 1 over M dP dt. Okay, so that's the famous Lamo's formula. Lamo's formula. Okay, note that all quantity in section 14.1 are real. Hence, that's this one. And in Jackson denoted as dP dt squared. Okay, that's Jackson notation. Now, that's the classical limit. V is very small. No speed. Okay. However, let's generalize this problem, this radiation, this power, total power radiated. Total power radiated. Let's generalize this one to 4th dimension. That's the relativistic generalization. The expression in equation 14.23 can be generalized to a relativistic form in which P will be a Lorentz invariant. Whoa, interesting. So it must be satisfy Lorentz transformation. So we first, that's P momentum. We change to 4 momentum, from 3 momentum to 4 momentum. 4. Okay, and from T generalized to tau. Tau is the proper time, it's Lorentz scalar. So this one, dP dt, changed to the capital P d tau. Therefore, P becomes this one. 2, so it's we can rewrite it into the product of 2 4 vector. Product of 2 4 vector. Remember, we have this equation before. P dot P. Sorry. A is a 4 vector. B is a 4 vector. Then A dot B will be invariant under Lorentz transformation. Okay. So P is a 4 vector, 4 momentum, and P dot P will be an independent of the, you can imagine if we have P dot P will equals to P prime dot P prime. Okay, the same, invariant. Okay, that's Lorentz invariant, will be a Lorentz invariant. And this P is different from this P. This P is total power radiated. So I'm sorry, this P is different from that P. Okay, the procedure is as follows. In terms of momentum and energy, it can rewrite into this form and convert it to a left frame by using d tau over dt. That's the left frame. Left frame. We can rewrite it into this form. That's very smart, because if you want to derive this equation, you can imagine how much work you need. However, we just generalize from Lamo's formula, and then with the special relativity, knowledge of the special relativity, we generalize this equation into this equation. And this equation, d tau, and we will change to our left frame. Left frame is this one, time dilation. Okay, so this is the frame. This is the frame converted to left frame. So in terms of t, 10, equation 10 agrees with the result derived directly from equation 14.14. So you have two choices. You can derive this equation from the very beginning, or you just use the generalized relativistic generalization. 狭义相对论的广义化。So 不是广义相对论。It's not general relativity. It's just a generalized the special relativity, the equation from low velocity to very high velocity. So the total power radiated is here, can be put in different form. That's the fundamental form. And remember, gamma is here. Gamma square, therefore, is here. And you can change from velocity to momentum. Okay, so gamma square is equals to 1 plus momentum square m square c square. Okay, in terms of momentum, gamma here will be 1 plus p square m square c square. Okay, so dE over dt is mc squared d gamma over dt. So the gamma is here, just shown here. Therefore, it's dp dt. So eventually, this equation becomes here, 1 over 2. So we have this term, m squared c squared, this one, dt. Okay, the gamma give us m squared c squared, no change. Then 1 over 2 becomes 2 here. And this one becomes minus 1 over 2. So it becomes here. And p squared becomes 2 m squared c squared dot dp dt. Okay, for the numerator here. So m squared. Oh, so we have, what do we have? This one is gamma. 2 cancel. P here. M divided by m squared. So we have m here. Gamma is here. So how about c squared? C squared cancel with c squared. So eventually we have gamma p over gamma m v dp dt. Okay, that's this part. And v over c is beta. Okay, so with this part exactly the same, but this part from energy to this one. That's another expression. Expression 11. Total power radiated is here in terms of gamma, p, beta, and p absolute value. This P is the, yes, P is P absolute value. I'm sorry, handwriting is difficult to type. It's much easier. dp dt. Sorry. Relax. That's the absolute value of P. Check out. So we can rewrite this equation again. Rewrite this expression to here, okay? To here, to this one. So this one, we know the another expression. You have expression 11, expression 10, but it's still not good enough because expression 11, we have gamma, we have P, we have beta. Too complicated. Can we simplify the notation? Too complicated, too much notation. Okay, so let's simplify the notation again. And P is here. P is, remember, P is in terms of gamma mv equals gamma mc beta. So it's mc gamma beta. Okay, so therefore P squared will be m squared. P squared will be m squared c squared. And length divided into two parts. One is beta times the gamma dt. The other is gamma beta dot. Okay, and squared. And this one is simple. This one is simple because the E is gamma mc squared. So E squared gamma squared, therefore dE dt will be mc squared the gamma dt. Okay, so m squared c to the fourth, but we have another c squared here. Another c squared, so eventually correct. And gamma is related to beta. So we can replace the gamma dt to gamma cubed beta dot. That's relatively simple. So I think you can derive this equation by yourself without any difficulty. Okay, so substitute everything to here. M squared c squared beta squared the gamma dt squared. And here 2 beta dot gamma, and this one, okay, no problem. And what else? And this term here, and last one is the gamma dt squared, and this one can be replaced with this one, gamma cubed beta dot. Okay, so this one the same, beta dot. We have beta dot is here. Oh, sorry, we have another one. Another one exactly the same. So it's beta squared minus 1. Therefore, 1 minus beta squared gamma squared. Okay. Sorry. Let me write it again. Gamma squared equals 1 minus beta squared, right? Okay. So beta squared minus 1 here. Beta squared minus 1 equals minus 1 over gamma squared. Okay, that's this equation. And what else? Gamma to the 6. Okay. What else? We have 3. Remember, this one can be replaced with this one. That's why it's beta dot beta dot. And this one can be replaced with this one. This one is the same. So we have beta dot beta dot, beta dot beta dot, and beta dot squared. So these two minus gamma to the 4th plus 2 gamma to the 4th. So we have 1 only, this one. And here we have gamma squared beta. And we can move gamma to the 4th to the front. And here we will divide it by 1 over gamma squared. And we will change to this form. So everything will be related to beta and beta dot. Beta and beta dot. So gamma to the 4th, m squared c squared, beta dot here, minus beta squared, just separate them. Okay. And this one can be rewrite into this one. Okay. How? Just the same idea. A cross B dot C cross D, and A cross A dot C B dot D minus A dot D B dot C. So this term, this equation. So if we have beta dot, we will have these relations. Beta cross beta dot. Sorry, too low. It's not clear. Sorry. A huge mistake. Okay, move on to here. These properties. Because the notebook and iPad, the size is not compatible. So I can see the symbol, the slide easily in the iPad, but it's not correctly shown in the notebook. And then substituting everything to here, we have another expression. Another expression again. Okay, together with this one. So we have actually 3 expressions, but normally we prefer 2 because this one is related to beta and beta dot as well as gamma. This one is related to gamma, p vector, beta, and p absolute value. And equation 10. This one is related to P and E. So 3 expressions, which one is more convenient? That depends. Let me show you. I will give you some example. The first example is linear acceleration. Here, linear accelerator, 线性加速器. That is, P is parallel to the accelerating force. Force is proportional to the change of P, and force is related to, let me show you, force is related to, that's the ordinary force. And now we assume momentum and force is the same, okay? That is, the particle move in this direction, and the force is also in this direction, the same, okay? So since they are in the same direction, so we don't have to worry about the direction. We can use this expression, equation 11. And since they are the same, so we don't have to worry, the same. Therefore, it becomes 1 minus beta squared dp dt squared, okay? 1 minus beta cancel with this one. Therefore, eventually we have this simple expression. And momentum, total power radiated. I'm sorry, we have too much notation here. P is here. dP dE, dP dE. Why dP dE? Because dP is here. Okay, the same. dE is the change of the energy equals F of dx. So force and displacement, that's the change of the energy. So dP dt equals, if we equate, just a moment. dP over dt is force. dE over dx is force. Therefore, they all equals to force. We can replace dP dt with dE dx. Oh, that's good. That's good. Why? That's good. So P divided by dE dt. dE dt, P is radiated power. E is externally supplied power by someone. You can change its energy. So you just give it power, but it will radiate. You accelerate the power, you accelerate the charge, and the charge will increase in energy. Energy change rate. You give it energy, and then it will radiate because accelerated charge will radiate. Next, externally supplied power, 外在的给的功率，这是 radiated power. Okay, so P divided by this one, so we have this one, and remember, this one can be separate to this one, together with this one. dE, dt, dx here, dx equals v dt. Okay, that's why we can change the notation. Okay, so we have 2e squared divided by 3m squared c squared divided by v dE dx. If the particle is very close to the speed of light, then this will become here E squared M squared MC squared divided by 3MC squared. That is 3.7 times 10 to the minus 15 meters per MeV. Very small. 3.7 times 10 to the minus 15 meters per MeV. Typically, if we accelerate a particle with this energy, 1 meter, we accelerate to 50. Length, this one times this one. This one times this one. So radiated power will be very, very small. It's negligible in the linear accelerators. Linear accelerator is good it's very useful because it can accelerate the charge, but the radiation is very small. Radiated power is very small. So we can convert the energy almost 100% to the charged particle. That's the first one. Second, if we have a circular accelerator, for example, synchrotron, let's use this equation again. And since it's constant motion, circular accelerator 绕圆圈的 and it's constant motion. No, not constant motion, circularly motion. Therefore, P will be very small. The absolute value will be almost constant, almost. And therefore, the contribution from this one is small. All we need is this one. This one will relate with 向心力, centrifugal force. So it's 2E squared, 3M squared, C cubed, the same, coefficient the same. Just this one. This is related to the accelerated force toward the center. So the P is in the c dot direction, momentum in the c dot direction. And P is a constant. So this part is small, negligible. Therefore, only this one, the E theta. But remember, E theta, the change in E theta will be, you can rewrite into this form. The E theta, the theta, the theta. Just enlarge this one and this one. So it will become, okay, E rho minus E rho. So it's a force toward this one, acceleration. The theta, the T, that is omega, angular frequency. So it becomes minus omega P E rho. And so the P dt will be absolute value, just one value, omega P. And omega is V divided by rho. V is the velocity. Remember, velocity equals to, sorry. Okay, that's angular frequency. P is gamma mv. Just substitute everything to this one. Substitute everything to this one. So eventually, what we have now. okay, from here. So omega can be right into V gamma rho square. Okay, let's learn exact expression for P if the particle is an uniform circular motion. But actually, for the synchrotron radiation, it's not purely circular motion, not purely circular motion. It's something like constant motion, change direction, change direction, change direction, change direction, change direction. When they change the direction, they use a magnet to bend, and then it will generate radiation here. Change the direction, generate radiation here. Change the direction, radiation. So let's bin line. That's the bin line. Okay, that's S-ray. Okay, so we will talk about synchrotron radiation very soon, very soon. So let's rewrite this equation again. P is equals to this one. So delta E is the radiation loss per revolution. 绕一圈能量损失多少? That will be total power 2 pi rho divided by P. That's the time. Period. Period. 绕一圈，用光速绕一圈，它花多少时间？好，花多少时间乘以它总共 total radiated power， 那就是功率的嘛，功率的变化。所以功率的变化会是这样子。The energy change rate will be here per revolution. That's huge. Huge. Okay, so you can imagine for 1 keV for early synchrotrons, that for early synchrotron, this value is very small, energy loss very small. But for 1.3 GeV, synchrotron radiation, National Synchrotron Research Center, that will be 72 keV, lost totally 72 keV, and so the charged particle will slow down, radiate, so it will slow down. Therefore, we need a cavity. We need a cavity like this one. Oh, sorry. We need a cavity to accelerate the particle, to gain more energy. It lost energy, so we should give it energy. And for a 10 GeV Cornell synchrotron, one revolution will lose 8.9 MeV. Huge energy, huge. Yeah. It also depends on current. So the total power radiated in a circular motion will be here, say in M, delta E, in terms of 10 to the 6, wow, huge, in terms of MeV. So total power radiated in circular electron accelerator will be this one. Therefore, if we have 300 milliamp, 0.3 M, then you will have just times this one, cross. I don't want Siri, cross, shut up. No, we don't need. Okay. No need. 不需要，不需要，不需要，请关起来。奇怪，我又没有叫 Siri， 它为什么会起来 ？Okay, so we have two. One is circular motion, the other is linear motion. Circular accelerator, the other is linear accelerator. Two different conditions. Let's consider other case. We still have 2 pages. Page 32. Okay, page 32. That's problems. If a charge is in uniform circular motion, equation 14.31, which one? 14.31, this one. Equation 14.31 is an exact expression for the total power at the radius. Show that the total power has the same value as viewed in the rest frame of the particle. We just shown that it should be Lorentz transformation. Follow the Lorentz transformation. Okay, how to do that? Consider an instantaneous position of the charge located at the bottom of the orbit. So the particle is performed circular motion, but at a given time, particle is here. So it's moved in this direction. And so we have two velocity. We have velocity move to the right, move horizontally to the right with velocity value v0, and the acceleration v perpendicular points vertically upward, v0 squared over r. So that's the acceleration a perpendicular. And rho is the radius of the circle. Rho is Lamo radius. Mu, it's circular motion, not always Lamo radius. Okay, mu in rest frame of the charge. If we move with the charge, what will happen? If we move, we have two frames. This is left frame. Left frame, you see a particle move circularly. But in the left frame, but in the rest frame, you move with the particle at a given moment in the same direction, v0. So you just side by side. It's rest frame. Therefore, we have C problem 11.5 in chapter 11. We have A parallel here. A perpendicular is here. We have derived this equation before, so we just use this property. So obviously, we know in this constant motion, therefore, parallel velocity parallel is 0. Therefore, convert to here is still 0, but perpendicular velocity will be different. So in this frame, we will gamma 0 squared A perpendicular in this frame, rest frame. This is left frame. 从实验室的角度来看，从粒子跟它一起运动的角度来看 ，the acceleration of the charge is vertically upward. the acceleration of the charge is vertically upward in both frames, and they are related here. Since the charge is at rest in frame K prime at rest, Lamo's formula, because B is very small, so we can use Lamo's formula. Lamo's formula here. We can strictly use Lamo's formula. So for this case, it's at rest, Okay, so we will use Lamo's formula. Lamo's formula, okay? That's good. That's E2E squared over 3C cubed, gamma squared, V0 to the fourth divided by rho. So we can rewrite into this form. Use this one, divided by this one, becomes beta, okay? This is the same power, build it in the left frame, this frame. See equation 14.31. The result here will be, no matter it will radiate, and all from here, rest frame, left frame, rest frame, they should be exactly the same. Total power radiated is consistent with the fact that total radiated power is a Lorentz invariant. That's interesting. The total radiated power is a Lorentz invariant. The total radiated power is a Lorentz invariant. However, the angular distribution of radiation will be different in the two frames. We will show later in next section, actually. That for the same acceleration, the angular distribution depends sensitively on particles' velocity. Depends sensitively on the particle's velocity. That's another issue. Just an advertise. Section 3, angular distribution of radiation emitted by an accelerated charge. So we use this equation over and over again. This equation comes from linear potential. And we use this property over and over again. Okay, that's the end. See you next time.